Building a massive enterprise-scale community platform requires balancing extreme data depth with high throughput write velocity before it fractures. On the read side, the platform must retrieve discussion threads nested dozens of levels deep, and it has to deliver these entire comment trees to the user with near zero latency. Simultaneously, the write side is being hammered by millions of concurrent users, triggering highly contentious operations, specifically upvoting and downvoting active content instantly. A standard relational database, like a naive PostgreSQL setup, attempts to handle this by writing every single vote directly to disk and retrieving comment trees by iteratively searching parent-child rows. This creates a failure state under heavy load. Row-level locks from the voting traffic cascade into massive queues, while the recursive database queries required to load deep comment threads time out, bringing the entire application down to a halt. Stability requires decoupling state management, adopting specialized models for hierarchical data, and using statistical algorithms for feeds. We cannot achieve enterprise scaling simply by provisioning larger database servers. The read path must be completely separated from the write path to eliminate contention. Before applying advanced caching, we first must eliminate the physical storage layer as a bottleneck. This diagram shows the database vertically sharded into 3 domains: identity service, subreddit directory, and core content. Identity and directory are strictly isolated. A viral post causing massive comment spikes stays contained, never consuming resources needed for global user logins. That still leaves the core content database handling the sheer volume of posts, comments, and votes. To manage this throughput, the tables must be horizontally sharded across multiple physical database instances. We need a sharding key that prevents queries from crossing between separate database nodes. For a community platform, the optimal key is the subreddit ID. When a user interacts, the system hashes the subreddit ID, routing the payload to a specific database shard. Because every record includes this ID, all community content lives on a single node, eliminating expensive cross-shard joins. Strict domain isolation and intelligent sharding ensure that volatile traffic in one specific community cannot degrade the stability of the larger platform. With the storage architecture distributed, we turn to the core read challenge, rendering discussion threads that contain thousands of comments across dozens of nesting levels. The standard model is the adjacency list, where each row points back to its immediate parent. Querying an adjacency list requires the database to execute recursive common table expressions, looping back over the table for every layer of depth. As a thread grows deeper, query latency compounds, severely degrading read performance. The enterprise solution to hierarchical data bypasses recursion entirely using the closure table pattern. The closure table decouples hierarchical relationships from the comments. A separate junction table records every path connecting any ancestor to any descendant, across all tree depths. Because every relationship is mapped, the system fetches entire subtrees using a single SQL join. Achieving this query speed requires a storage trade-off. Mapping deep trees consumes massive storage. In read-heavy systems, database storage is cheap, but compute time is incredibly expensive. Trading storage overhead for guaranteed O1 read performance is a necessary mathematical compromise. Extracting comment trees solves the read latency, but we still face write contention. User votes are the most frequent volatile operations. If thousands of users upvote a viral post in the same second, writing directly to a database creates a massive traffic jam of row-level locks. We resolve this by placing an in-memory buffer between the user and the database, known as a write-behind caching architecture. A Redis cluster maintains specific memory structures for every post, sets of upvoting and downvoting user IDs, and a hash tracking net score. To prevent race conditions from concurrent updates, atomic MUA scripts execute within a strict single-threaded context, safely processing state changes. Once Redis updates the score in memory, the API gateway publishes a message representing the vote to a RabbitMQ or Kafka partition. A dedicated pool of backend workers monitors these queues, pulling the vote events asynchronously. Rather than writing each vote individually, workers execute write coalescing. They group thousands of events over a short time window and run bulk upsert queries. Decoupling state transitions into an asynchronous memory queue guarantees microsecond API response times, completely shielding the user from the underlying database throughput limits. An optimized, highly concurrent database means nothing if the application cannot surface high-quality content dynamically. Calculating a post's score by simply subtracting downvotes from upvotes creates stagnant feeds. Old posts with massive vote totals will permanently sit at the top. The platform uses the hot sort algorithm to evaluate posts, surfacing rapid, early community engagement. This logarithmic curve illustrates the hot sort algorithm weighting early traction. The first 10 upvotes carry the exact same algorithmic weight as the next 100. Concurrently, a chronological premium actively degrades older posts, forcing them off the front page to ensure fresh content cycles. Ranking comments presents a distinct challenge. Applying the hot sort here creates an insurmountable first-mover advantage, where the very first reply gathers all visibility. Ranking comments by pure positive percentage is mathematically flawed. A comment with 1 upvote and no downvotes has a 100% ratio, outranking a highly engaged comment with 100 upvotes and 2 downvotes. The platform solves comment sorting by applying the Wilson score confidence interval. This distribution curve shows the Wilson algorithm treating votes as a statistical sample. By ranking comments using the lower bound of this interval, the system strictly penalizes small sample sizes, preventing untested opinions from jumping ahead of proven high-engagement discussions. Algorithmic visibility requires advanced statistics. By mathematically compensating for chronological biases and small sample sizes, the system surfaces actual quality instead of just early arrivals. An enterprise-scale community platform operates as an orchestrated assembly of highly specific data pipelines, engineered to bypass distinct bottlenecks. We can now step back to view the macro architecture in action, processing massive concurrent data throughput at incredibly high speeds. When a user votes, the action bypasses the database entirely. It hits a single-threaded Redis-Lewis script to update the state instantly, triggering an asynchronous Kafka event to be grouped and stored later. When a user loads a page, the read query hits a horizontally sharded database to fetch a comment path from a closure table before routing the output through the Wilson score for statistical sorting. Scalability at this level requires abandoning monolithic thinking. Managing millions of concurrent users means engineering dedicated, mathematically precise pathways for every specific constraint of the domain.